Okay, hello, my name is Brett, and today I want to lecture about diode essentials. This lecture will be referencing Microelectronic Circuits 8th edition by Cedra and Smith. It's an excellent book for this topic. In this video, we will cover the following topics: the ideal diode, terminal characteristics of junction diodes, constant voltage drop model, and throughout the video we'll do some examples. I'll include timestamps to each of these topics in the description. So let's get started. So what is a diode? The diode is an essential circuit element for nonlinear circuits. For many people, this is their first introduction to nonlinear circuits, and it's commonly used in rectifier circuits, AC to DC conversion. So for example, if I have an AC signal, but let's say I only want this top half of the signal, I can use a diode so that I only see the upper peaks. This down here is what a diode looks like in circuit analysis. It has two terminals, an anode and a cathode. So that the anode enters the triangular side, and then the cathode is from the straight line side. Now, unlike a resistor that also has two terminals, and it just has a linear relationship between the current and voltage, right? V equals IR. That is not the case for diodes. They have a nonlinear relationship between the current and voltage, and we're going to explore that in this video. So this is the ideal diode model. There's a lot of content to cover in this slide, but the first thing I want to pay attention to is we describe the voltage drop across a diode as the voltage from the anode to the cathode. We see the positive terminal is the anode, the negative terminal is the cathode. Now let's focus on this reverse bias region. So if the voltage across a diode is less than 0, for example, 5 volts to 10 volts, this would be a voltage drop of negative 5 volts. This would signify the reverse biased region of the diode. So the voltage at the anode is less than the voltage at the cathode. I like to think of this as going from low to high, low voltage to high voltage. And in the reverse biased region, the diode will behave like an open circuit. Current equals 0. We usually also call this the cutoff region. So you can see this is what the diode would look like in the reverse bias region, just an open circuit. The voltage is negative and there is 0 current because it's like an open circuit. And you can see in this graph here, the reverse bias region, when voltage is less than 0, we see no current. Now, there's the second region, the forward bias region. We see that if the voltage at the anode is greater than the voltage at the cathode, for example, 5 volts to 0 volts, we can describe this as high to low, 5 to 0. In this case, the diode behaves like a short circuit and it will conduct current. So the voltage drop is 0 and it will behave like a short circuit conducting current. So we can see that in the forward bias region. Let's try some examples to really understand this. In this slide, we're going to try to demonstrate the biasing regions. So let's look at this left circuit. Observe the diode, right? In order to determine if it's forward biased or reverse biased, you want to see what the voltage is at the anode and at the cathode. Now we know that there's this resistor, but we can ignore it for now. We just want to see what is the observation. So from the anode, we have 10 volts. The cathode is grounded to 0 volts. So you can see we're going from 10 volts to 0 volts. high to low. So in this left circuit, the diode is forward biased. So we can see that the voltage drop is 0 because it's behaving like a short circuit. Therefore, it conducts current. So that means that the entire voltage drop is occurring across this resistor. All the 10 volts are being consumed by the resistor. Now let's look at the right side. Okay, let's try our diode again. So we can see that the anode is now the bottom and is being grounded to 0 volts. The cathode observes 10 volts. So this time we're going low to high. So this diode is reverse biased. Therefore, the current equals 0. Whenever you have a diode and you read its reverse bias, you can almost always just immediately state that the current equals 0. Because of that, remember that this diode is now behaving like an open circuit. In college, my professor always explained an open circuit to act like a giant resistance, infinite resistance. And because of that, that makes this 1 kilo ohm resistor very negligible compared to the open circuit. So the resistor is not taking any voltage. All voltage is being consumed by this reverse biased diode. Now this is a rectifier application. So we have an input voltage, we have a diode, then we have a resistor, plus minus Vout. So this is a lot closer to a real-life application of a diode. So we can see we have this sinusoidal signal for our V input with a peak at Vp. Let's try to sketch the waveform of the output voltage. So, in order to understand that, let's try to figure out our two cases. What does Vout look like when Vi is greater than 0? So for example, we'll just say that V peak is equal to 5 volts. So if Vi is at the peak, we go immediately to the anode, 5 volts. And what is the cathode? Well, the cathode, we see, is connected to this terminal, to this resistor, to this terminal, and then to ground. Therefore, we can state that the cathode observes 0 volts. So because of that, we're going from high to low. So the diode will be forward biased. And we recall, in the forward bias region, this diode will behave like a short circuit, consuming 0 volts across of it. And what that means is the resistor will take the entire voltage from Vi. So that means Vout will equal to Vi. But what about when Vi is less than 0? So again, that would be like going from negative 5 volts to 0 volts, low to high. That would mean that the diode is reverse biased and acts like an open circuit with infinite resistance, making this resistor negligible. We know it will conduct 0 current and it will consume all of the input voltage, leaving no voltage left at this node for this resistor. Therefore, Vout will be 0. So if we want to sketch Vout, well again, when V in is positive, it's equal to V out. So we'll see these positive peaks, and it will achieve the entire value of V in. So we're going to get the same peak value. And then when V in is negative, V out just equals 0. So this is our waveform of V out. We only see the positive values. The diode has essentially rectified or cut off the negative values of V in. Let's do a couple of examples. We want to sketch the transfer characteristic of V out versus V in. That essentially just means if V in is on the x-axis, what does V out look like? Well, as we just stated, when V in is greater than 0, V out is equal to V in. And when V in is less than 0, V out equals 0. So if I try to sketch the transfer characteristic, when V in is less than 0, we have 0 volts for V out. Then as soon as we surpass 0, V out just equals to V in. So this would just be a linear relationship with a slope of 1. Now we want to do problem 2. Sketch the waveform of the voltage across the diode VD. Okay. So let's do our two cases again. When Vi is greater than 0, what is the voltage across the diode? Well, we know that the diode is forward biased, which means that the voltage will equal 0 because it's behaving like a short circuit. Now when Vi is less than 0, we know that the diode is reverse biased, which means it is consuming all of the input voltage because it is behaving like an open circuit. So what we see is essentially the inverse relationship to Vi. We see that when Vi is greater than 0, V out equals Vi, and Vd equals 0, and vice versa for when Vn is negative. So therefore, we will just observe the negative peaks for Vd. All right, let's continue. Let Vn have a peak value of 10 volts and R equal 5 kiloohms. First question is to find the peak value of the current. So we know that, again, when the diode is reverse biased, the current will be 0. So our peak value will be when the diode is forward biased, which is when Vi is greater than 0. Naturally, this will be when Vi is at its peak value. So 10 volts and 5 kiloohms here. So we can just do some nodal analysis, right? Since V is equal to I times R, I is equal to V divided by R. So I is equal to 10 volts divided by 5 kiloohms, which is equal to 2 milliamps. Now as for the DC component of V out, what that's asking for is, if this is the DC component of V in, it's essentially just the average value. This would be the DC component of V in, for example. Now the average value for a sine wave is, for a sine wave, it is V peak divided by pi. So therefore, the DC component of V out will be 10 volts divided by pi. That is equal to 3.18 volts. Okay, let's move on to the next topic. Example 2. Find the values of current and voltage in the following circuit. And we're going to assume an ideal diode. So I always start out by drawing the diode. And we want to observe the voltage at the anode, the voltage at the cathode. So for the anode, we're observing positive 5 volts, and for the cathode, we are observing a ground voltage of 0 volts. So we're going from high to low. Therefore, this diode is forward biased, which means the voltage across the diode is equal to 0. The diode will conduct current, so I will just be equal to 5 volts divided by 2.5 kiloohms, which is equal to 2 milliamps. Okay, let's do this circuit. We observe that the anode observes 0 volts, the cathode observes positive 5 volts. Therefore, we're going from low to high, 0 to 5. So this diode is reverse biased. That means I can immediately state that the current is 0. And this diode will behave like an open circuit, consuming the entire voltage across this wire. This 2.5 kiloohms will essentially be negligible because the diode will observe a resistance of infinite. So V is equal to 5 volts. Okay, let's do this one. So the anode observes negative 5 volts. The cathode observes 0 volts. Now you want to be careful with these negative values. Negative 5 is less than 0. Therefore, we're going from low to high. So this diode will be reverse biased. So again, I can immediately state that the current equals 0. And this diode will consume the entire voltage drop from 0 to negative 5. So that's a 5 volt drop from 0 to negative 5. Okay, this should be the last one. Let's draw the diode. The anode observes 0 volts. The cathode observes negative 5 volts. Again, you got to be careful. 0 is greater than negative 5. So we're going from high to low. So this diode is forward biased. Therefore, the voltage drop will be 0. And the current will be 0 minus negative 5 volts divided by 2.5 kiloohms. So that's basically just 5 divided by 2.5 kiloohms, which is 2 milliamps. Okay, that concludes the ideal diode section. Let's move on to terminal characteristics of junction diodes. So you can see in this graph, we have a bit more of a complicated relationship for the diode. Again, we have the forward biased region, and we have the reverse biased region. But we've also added this breakdown region. We're going to study each region carefully, but what I want to point out is that the diode is still pretty similar to the ideal diode model. But this is going to give us a lot more accurate understanding of how the diode behaves in the real world. So let's dive into the forward bias region first. So again, in the forward biased region, we're going from high to low. And if you want to calculate the current, we have this important formula. I is equal to I sub s times e to the power of v divided by v sub t minus 1. Now, what are all these values? So I is just the current traveling across the diode. I sub s is a important constant for a diode. It's called the saturation current or scale current. Each diode model that's manufactured has a different value of IS. But what you want to know is that it's usually extremely small, like 10 to the negative 16 amps. That's small. Now V is the voltage across the diode. Now in the ideal diode model, V would always equal 0. But what you're going to find out is that usually V will actually be closer to a 0.7 voltage drop in the real world. And we'll get to that concept shortly. Now VT just stands for the thermal voltage. It's a semiconductor property and it usually equals 25 millivolts at room temperature. You can change this formula around to solve for the voltage across a diode by V equals VT times the natural log of the current divided by the saturation current. This is another formula you may use. If you have two voltage records at two different currents across the diode, you can solve for the change in voltage. Okay, let's try example 3. So we have a silicone diode said to be a 1 milliamp device, displays a forward voltage of 0.7 volts at a current of 1 milliamp. So that's saying we have a 0.7 volt drop with a current of 1 milliamp. And we want to find the value of the scaling constant, I sub s. So remember, I is equal to Is times e to the power of v divided by vt minus 1. Now, to make this problem even simpler, we can actually rewrite this equation to eliminate the minus 1. This minus 1 is going to be very negligible. You can even try it out for yourself. But if we want to isolate Is, it would just be I divided by e to the power of v divided by vt, which is equal to I times e to the power of negative v divided by vt. So that would be 1 milliamp times e to the power of negative 0.7 volts divided by 25 millivolts. And that is equal to 6.9 times 10 to the negative 16 amps. And if we want to repeat this problem for a 1 amp diode, that would be Is is equal to 1 amp times e to the power of negative 0.7 volts divided by 25 millivolts. That is equal to 6.9 times 10 to the negative 13 amps. Okay, let's try out this problem. Find the change in diode voltage if the current changes from 0.1 milliamps to 10 milliamps. So remember, we have this formula V2 minus V1 equals Vt times the natural log of I2 divided by I1. And we're finding the change in diode voltage. So that would just be delta V, which is equal to V2 minus V1. So this is what we're solving for, the left side of the equation. We're going to say that I2 is equal to 10 milliamps and I1 is equal to 0.1 milliamps. So the change in voltage is equal to 25 millivolts. That's a natural log of 10 milliamps divided by 0.1 milliamps. This is equal to 120 millivolts. Okay, now let's discuss the reverse bias and breakdown regions. So again, in the reverse bias region, negligible current passes through the diode. In most models, it's usually equal to the negative scaling current, which, as we just demonstrated in the last example, is extremely small. So in most problems, you can just say it's 0 amps. However, it is possible that the magnitude of the reverse voltage is so large that it achieves what we call a breakdown voltage, V sub BR, and it enters the breakdown region. And so current will decrease exponentially in the breakdown region. We won't study this breakdown region too closely in this video, just know that it exists. So this is where we develop the constant voltage drop model, and it is the best way to efficiently model a diode without making things too complicated. It's very similar to the ideal diode model, but we're going to change two things. So now, instead of entering the forward biased region at 0 volts, it's going to happen at 0.7 volts. The other thing is that when we enter the forward bias region, instead of having just a 0 volt drop and acting like a short circuit, the diode will now experience a voltage drop of 0.7 volts. Otherwise, it behaves quite similar to the ideal diode model. Let's try it out with some examples. Using the constant voltage drop model, find ID and VD for the case VDD equals 5 volts and R equals 10 kilo ohms. So we know that this bottom wire is essentially grounded. So if we observe the diode, we're going from 0 volt at the cathode. At the anode, VDD is 5 volts, so we're going from high to low. So this diode is forward biased, and because we're using the constant voltage drop model, that means VD equals 0.7 volts. And the current will just be equal to, now we have to take note of this diode. So this is 5 volts, and here we have 0.7 volts. That means the current will be 5 minus 0.7 divided by our resistance of 10 kilo ohms, which is 0.43 milliamps. So be wary of that additional voltage drop when you're calculating the current. I have a playlist on my channel with many walkthrough solutions from the microelectronic circuits textbook. Chapter 4 is all about the diodes. So for more practice, please refer to my walkthrough solutions there. Thank you for watching my lecture. For any queries, comments, or concerns, you can contact me via my email. And I hope to see you in another video.